The concept that we're going to have a look at today is called normalization. It is one of the important pre-processing steps before you implement a machine learning algorithm onto your data set. So before understanding what normalization is and why do we use this, let's have a look at a problem. Over here, I have a sample data set, which is recording the age and income of different persons, different people. And it is also recording whether or not these people made a purchase, right, for your business. Right? So from a machine learning point of view, you can look at it as a problem where you are trying to predict whether or not a person is going to make purchase depending on what their age and income is. Now I understand that in actuality, this decision is going to depend on different types of features, not just age and income over here. But for the sake of simplicity, let's just consider age and income right now. Okay. So there are a lot of machine learning algorithms which makes use of proximity or the distance measured in order to do this prediction, right? An example being K and N, right? K nearest neighbor is a very prominent example of a machine learning algorithm which uses distance metric in order to figure out whether or not this purchase is going to happen or make any prediction, right? So one of the metric that we can use, the distance metric, is the Euclidean distance, right? And this is represented by root of x2 minus x1 the whole square plus y2 minus y1 the whole square, right? So imagine that a new person comes along into this data set. He is about, let's say, 40 years old and is earning about 60,000, let's say, right? And he has made that purchase. Okay. Let me not say that he has made the purchase. My intention is to make this prediction actually, right? So if I'm going to implement this KNN algorithm onto this, my first step would be calculating the distance of this new data point from the existing data points, right? Plugging this thing onto my Euclidean distance, let me say I'm trying to figure out how far away or how different this person is from the first person. Okay. In this case, what I would have to do is x2, that is 40, minus 25, the whole square, plus 60,000 minus 30,000, the whole square, right? Perfect. And this, if I break it down further, is going to be what? 15 square plus 30,000 square. Now, I'm not going to calculate this for you because the problem is going to be evident just from this state here. So whatever this result is going to be, I want you to understand that the contribution made by the age factor over here is 15 square units, right? On the other hand, the contribution being made by the income factor is 30,000 square units, right? That difference alone should give you a good intuition as to what the problem is, right? The contribution of my age factor is being overpowered, it's being overshadowed by the income factor just because of the fact that my income is being recorded in higher scale, right? But that does not mean that income is more important than age, right? Or that age is less important than income. Okay. Right now, my age is being overpowered just because of the factor of scale over here, because it is natural to record age in a lower scale than income, right? So this is the problem that normalization is going to solve for. What normalization refers to is the process of scaling down the features and bringing them to a comparable range. That is to say, I want to scale down age and income and somehow preserve the information that it is giving me and still be able to carry out this prediction, right? That is what normalization is all about. Simply put, it is scaling down the features. Now, there are a lot of different ways that you can carry out this normalization, this carrying out this scaling down of the features, one of which is the min-max scaling. Let's have a look at how min-max scaling works. Right. Min-max scaling states that your transformed variable value is going to look like this. That is x minus x minimum divided by x max minus x minimum. I want you to take a time, pause this video, look at this formula and try to understand what it is doing to your features. Let's try to scale down this data point 25 from age, right? Plugging this into the equation, I'm going to get that it is 25 is my x minus x minimum. That again is 25 only, divided by 50 minus 25, right? But since this becomes 0, your value would over here be 0, right? If I am going to do scaling for this particular data point, what is that going to look like? It's basically going to be 45 minus x minimum is 25 divided by 50 minus 25. That is again 25. Right. So this is going to give you 20 over 25, which is basically 4 over 5. Right. That is going to be about 0.8. Right. So the idea is your 45, this particular feature is going to get scaled down to the value 0.8. Right. Similarly, you can apply the same methodology to your income as well. Let's try doing that. Let's say my x over here is 30,000 minus the minimum of the salary is again 30,000 itself, divided by whatever that number is. It's going to be 1,20,000 minus 30,000, but it is going to become 0. Right? Let's look at 1,20,000 and see what that is going to happen. So when you plug in 1,20,000 over here into the equation, this is going to become 1. So you might have got this intuition from here. Your min-max scaling is going to scale your feature in the range of 0 to 1. It does not matter what your scale of, what is the original scale over here. After the conversion, everything is going to exist between the range of 0 and 1. Right? Finally, let's do this for 5,000 as well. If you plug in 5,000 in this place, I'm sorry, that is 50,000, not 5,000. You're going to get about 20,000 over 1,80,000. Sorry, 1,20,000 minus 3,000. 30,000 is going to be 90,000. And 2 over 9 is basically 0.2. This is how you are going to carry out min-max scaling, right? So at this point of time, a natural question might occur to your mind that if I'm doing this scaling to the features, is it not possible that the relationship between the feature is going to get disrupted, or the information that my age and income is trying to convey, is that going to get disrupted, right? Let's have a look at that. Over here, I have plotted for you the age and income where it was in the original scale, right? Age is in the scale of 25 to 50, and income in the range of 40,000 to 1,40,000, right? So this is what it was looking like previously. And even after you scale the things, right? I have normalized the age over here. Now it is existing between the range of 0 to 1, and your income is also existing between the range of 0 to 1 over here. But you would see the relationship, right, is still preserved. There is no disruption in the relationship between these two. And now the advantage is, since both age and income are measured in the same scale, right? No such feature is going to be able to overpower or overshadow the decision when you are calculating the distance metric or any similar kind of a process, right? So that is the intention of doing normalization. In order to look at the rest of the normalization technique, as I mentioned previously, this is not the only normalization technique that you have in hand. There are many more, and we would be doing more videos to cover those in detail. So stay tuned. Thank you.